Everything we built, from the phone in your hand to the tallest skyscrapers, it all starts as just an idea. But how do you take that idea and turn it into something real, something built by thousands of people, where there's absolutely no room for error? Well, the answer is pretty incredible. You need a universal language, and that's what we're going to dive into.
I mean, just look at this. The complexity is just staggering, right? Every single component has to be flawless. One tiny misunderstanding, one misplaced decimal point, and you could have a disaster on your hands. So how on earth do engineers get that vision that's in their head into the hands of the builders perfectly intact?
Well, the answer is surprisingly simple, but also incredibly powerful. They use a language. Now, I'm not talking about a spoken language, but a visual one, designed from the ground up to be totally precise, completely unambiguous, and understood by anyone, anywhere. And that right there, that's the core principle. The whole point is to create a document that is so crystal clear, it's basically a legal contract for building something. There's no room for, oh, I thought you meant no. It's all about precise execution. So let's get into it and break down the rules of this language.
Okay, so just like any language, this one needs rules, right? A kind of shared grammar, so everyone's on the same page. And for engineering, you better believe creating that grammar was a super meticulous process that took decades.
At the very heart of it all is the technical drawing. Think of it as the ultimate instruction manual. And let's be clear, this has nothing to do with being artistic. It's all about absolute, total clarity. Every single line, every symbol has one exact, unchangeable meaning, period.
So where does that clarity come from? It comes from standards. And you can see here how those standards evolved, just taking the UK as an example. For more than 70 years, this one document, BS 308, was basically the Bible for designers. But, as technology marched on, the language had to keep up. That eventually led to a whole new global standard back in 2000. It was this constant, careful process of refinement.
And this is the basic grammar we were talking about. Super simple, but so smart. A solid line? That's an edge you can see. But a dashed line, that lets you see through the object to a detail that's hidden inside. A chain line marks the exact center of something. It's such an elegant system, isn't it? You get a ton of information with just a few simple types of lines.
Okay, so check this out. Here's how it all comes together in a real professional drawing. This is a fuel injector. You can see it right there. The solid outlines, those dashed lines showing the hidden channels deep inside, and the center lines marking every single circular part. It's literally a complete visual story, told without using a single word.
Now, for decades and decades, this language was written by hand on giant drawing boards. But then, the computer arrived, and it didn't just change the tools, it fundamentally transformed the language itself.
Yeah, the shift to computer-aided design, or CAD, it was nothing short of revolutionary. Manual drafting was painfully slow. Making one little change could take hours. With CAD, a whole day's worth of revisions could suddenly be done in minutes. But the real game changer, the thing that blew everyone's mind, was the jump from flat 2D drawings to interactive 3D models.
Because CAD wasn't just a faster pencil, it was a whole new way of thinking. Engineers went from just representing objects in 2D to actually solving problems in 3D. For the first time ever, you could spin a component around on your screen, you could look inside it and see how everything fit together virtually, all before a single piece of metal was even cut. This just unlocked so much potential. It was like giving engineers superpowers. Suddenly, they could run virtual stress tests to find weak points before anything was ever made. They could check for clashes, like making sure a pipe doesn't run straight through a steel beam inside a wall, all with the click of a button. And best of all, the digital design could be sent straight to a machine to be manufactured. It was just a monumental leap forward in both speed and accuracy. But wait, the evolution wasn't over yet. Not by a long shot. The next big step was to make the model itself intelligent, to turn it from just a drawing of shapes into a rich, living database of information.
And that brings us to something called BIM, or Building Information Modeling. Now, BIM isn't just a piece of software. It's a completely new way of working. The whole idea is to create one single shared digital model that holds not just the shape of the building, but tons and tons of information about it.
And this is the absolute key to understanding it. In a BIM model, a wall isn't just a couple of lines that make a rectangle. The model knows it's a wall. It knows what it's made of, its fire rating, how much it costs, even when it's supposed to be installed. It's a living database that everyone on the project can access and update in real time.
So, okay, if you have all these different people, architects, engineers, builders, all working on one single model, you're going to need a new rulebook, right? And that's exactly what the BIM Execution Plan, or BEP, is. It's the master plan that makes sure everyone is playing on the same team. It clearly lays out the goals, who's responsible for what tools to use, and exactly when those big milestones need to be hit.
Basically, the BEP wrangles every single part of a modern construction project: the people, the processes, the technology. It gets everything lined up under one set of standards to make sure the project is a success. You can think of it as the ultimate project management tool for our digital world.
All right, so we've gone on this incredible journey from simple paper drawings all the way to these intelligent databases. So now for the fun part. Let's see what this powerful new language actually lets us build. And trust me, the results are, well, they're pretty incredible.
This shared language has truly empowered engineers to work together across the globe and to take on challenges that were just impossible, even a generation ago. We're talking about everything from creating mind-bending structures to literally saving lives. Okay, just look at the Falkirk Wheel in Scotland. It's the world's only rotating boat lift. I mean, can you even imagine the precision it took to design and build this thing? It's a moving sculpture that has to balance these immense weights with really complex mechanics. It's a perfect example of what modern design tools make possible. It's part machine, part sculpture, and just pure engineering genius.
Here's a wild idea for you. What if to protect a building from an earthquake, you didn't try to make it stronger, but instead you just disconnected it from the ground? Well, that's the wild idea behind seismic base isolation. The entire building literally sits on these giant flexible bearings that absorb the shock. Trying to simulate those kinds of complex forces, you can only do that with today's digital tools, and this technology is absolutely saving lives.
And this design language isn't just for cool structures. It's now being used to tackle our absolute biggest challenges, like climate change. Right now in the UK, engineers are building the first ever carbon-negative road. How? By using these intelligent models to optimize the design and materials so perfectly that the project will actually absorb more carbon than it produces. I mean, that is what designing for the future looks like.
So, look how far we've come, from paper to pixels to these super intelligent models that live in the cloud. Every single step on this journey has unlocked a whole new level of human creativity. And it really leaves you with a fascinating question, doesn't it? As our design language keeps evolving, what will we be able to imagine and what will we be able to build next?